Hello everyone, welcome to another physics recap video from JEE Mantra 2025 series. In this module, we will be discussing three chapters: ray optics, wave optics and dual nature of radiation and matter. Not to the waste time, moving to the very first chapter, that is ray optics. Alright, so here, first of all, we need to discuss about law of reflection. You all know that what is law of reflection. What it says: angle of incidence is equal to angle of reflection. Incident ray, reflected ray and the normal lies in a common plane. Fine, a simple statement. Now, while discussing about the reflection, we have got the very first reflecting surface as the mirror. Okay, so you all know that mirror is a very smooth surface that can reflect or that can send back almost all the light striking on its surface. So here, while discussing about mirror, first we have to discuss about plane mirror. Alright, so while discussing about the plane mirror, the important thing that we need to understand is first thing about the size of the image. Okay, the size of the image will be same as that of what? Size of the object. That's point number one. Point number two, it's about the magnification. Magnification means it's a comparison of the size of the image as well as size of the object. So magnification basically the ratio of size of image upon size of object. So in this case, magnification is equal to what? Unity, that means 1. That means the size is same. Next is distance of the image. Distance of the image as well as distance of the object relation. Okay, so since this is a plane mirror, the distance of the image will be same as that of distance of the object with respect to the mirror. Alright, and next one is about the nature. Okay, so the image formed by the plane mirror, that is virtual as well as it can be real also. Fine, I repeat, the image formed by a plane mirror can be a real image as well as virtual image. If the object is real, I repeat, if the object is real, then the image will be virtual. And if the object is virtual, then the image will be real. Alright, and the last one is what should be the size of the image? Sorry, what should be the size of the mirror so that a particular person can see his complete image. Okay, so exactly it need to be half of the height of the person. That means if capital H is the height of the person, then he must have a plane mirror of length L that is equal to H by 2 so that he can completely see his image in the mirror. Alright, moving to the next slide, that is all about the number of images that can be formed by two plane mirrors kept at an angle of theta. So basically what we do is that we take the ratio 360 degree divided by angle theta, where angle theta is nothing, like this is mirror number 1 and here this is mirror number 2. These two mirrors are kept at an angle of theta. So first of all, we will be taking 360 degree divided by theta and we check whether it is an even number or odd number. I repeat, even number or odd number. And if it is coming as an even number, okay, if it is coming as an even number, then the number of images formed is going to be 360 divided by theta minus of 1. I repeat, if it is an even number, it's going to be 360 divided by theta minus of 1. This is applicable in both the case where the object is kept symmetric or unsymmetric with respect to the mirror. Symmetric as well as unsymmetric means this is the axis of symmetry. The object is exactly placed over here, that means symmetric. If it is placed somewhere here or somewhere here, that is kept unsymmetric. Okay, so in both the case, this formula is applicable, that is 360 divided by theta minus of 1. And if it is an odd number, then we will write it as 360 divided by theta. Alright, so I told you there are two possibilities where it can be symmetric as well as unsymmetric. So if this is an odd number, then 360 by theta, alright, 360 by theta if it is unsymmetric. And if it is symmetric, then it has to be 360 divided by theta minus of 1. Alright, I repeat once again, if it is an even number, it's 360 by theta minus 1, both the case symmetric as well as unsymmetric. And if it is an odd number and symmetric, then it is 360 divided by theta minus 1. And if it is again odd number, all right, then asymmetric, then it is 360 divided by theta only. All right. So that is how we find out the number of images formed by two mirrors kept at an angle of theta. All right. Next is, what if the plane mirror is rotated through an angle theta? Through what angle the reflected ray will be rotated, provided object position is not changed. Okay, so keeping the object as stationary, if the plane mirror is rotated through an angle theta, then the reflected ray will be rotating through an angle of 2 times theta. If it is the mirror is rotated through an angle theta, all right, where it is? Yes, it's rotated through an angle theta, then the reflected ray that will be rotated through an angle of 2 times theta. All right, and next one is of about the focal length as well as the power of plane mirror. You all know that the focal length of the plane mirror is what? Infinity. All right, and what about the power? Power is 0. Basically, the power as well as focal length, as you know that focal length, we find out if the rays are coming from infinity, where it is converging or seems to be diverging from a point, as for if from any reflecting surface is concerned. So for a plane mirror, no diverging or no converging is happening in the case of plane mirror. So just because of that, the focal length is going to be what? Infinity. And since this diverging as well as converging is not taking place, the power is considered as 0 only. All right. Next is, in the image formed by the plane mirror, there will be a lateral inversion. All right. That means if I am having an object in this shape, the image formed in the plane mirror is going to be something like this only. All right. So here this is the plane mirror. So this lateral inversion will definitely be there. All right. So that has to be taken into consideration while dealing with the image formed due to the plane mirror. All right. Fine. Moving to the next, that is spherical mirrors. While discussing about spherical mirrors, we have got 2 type of spherical mirrors. First one is concave mirror, as well as next one is convex mirror. You know basically what is the difference between these two. Moving ahead with the important terms as well as the relations, first of all we have to discuss about the center of curvature. So you all know that the spherical mirror is formed from a part of a hollow sphere whose one side is highly polished, okay, to make it a reflecting surface. So the sphere out of which such a reflecting spherical mirror is made, the center of that sphere is known as the center of curvature. I repeat, this mirror is made from a hollow sphere. All right. So the center of that hollow sphere is considered as what? Center of curvature. All right. The next term is radius of curvature. So I just told you about one sphere. The radius of that sphere is known as what? Radius of curvature. Next is pole, the exact center of the reflecting surface. Okay, that is known as the pole. All right. Next is focus. If we are having light coming from infinity and moving parallel to the principal axis, so you might be wondering what is principal axis? Nothing. The line that joins the focus as well as pole is known as the principal axis. So any light rays which is coming parallel to the principal axis, it's either after reflection, it either get focused on one particular point on the principal axis, or it seems to be diverging. It seems to be diverging from a point on the principal axis. Okay, so it seems to be converging onto a point axis, that is for concave mirror, and seems to be diverging from a point on the principal axis, that is for convex mirror. Okay, so these 2 points separately for concave as well as convex is known as what? The focus. And next is focal length PF, that is P for pole and F for focus. So distance between P and F is known as what? The focal length. Next is relationship between F and R. F is equal to R by 2, that is the relation. And the last one is power of a mirror. That means if we have a spherical reflecting surface with focal length as F, then the power is supposed to be P equal to 1 by F. That is the relation over there. Moving to the next, that is mirror formula. So once we are having a spherical reflecting surface, and if I have U as the object distance, V as the image distance, and F as the focal length, then the relation connecting V, U and F is 1 by V plus 1 by U equal to 1 by F. I already told you what is F, U and V here. Now, next is linear magnification. Linear magnification in case of a spherical mirror. So, linear magnification means basically it is size of the image upon size of the object. So, I am having that relation over here. M is equal to I by O. I means size of the image and O means size of the object, and that is equal to minus of V by U. That is the very first relation. Okay, so this is about what? Linear magnification. Next is aerial as well as axial magnification. Aerial magnification means I am having a frame like this of say area A suffix O. Alright, and the image formed is like this. Let that be A suffix I, area of the image. Alright, so here this is the area of the image, and here this is area of the object. So area of the image upon area of the object, that is known as aerial magnification. I repeat, area of the image upon area of the object, that is known as aerial magnification. So how we find out? That is nothing, it's M square, that is V by U the whole square. I repeat, V by U the whole square. That is how we calculate the aerial magnification. Moving to the next, that is axial magnification. Axial magnification means if you are having a spherical mirror like this and an object is kept in this way, and let this length of the object be say du, and the length of the image formed here, let it be dv. Okay, so in that case I can say the relation is going to be minus of dv by du. dv by du, that is again v upon u the whole square. This is a basic relation. Now if I want to change v in terms of f or u in terms of f, then I have got a provision as f upon f minus u the whole square. That means here small letter v got replaced, and here this is f minus v upon f the whole square. That means here small letter u got replaced. That's as simple as that. Moving to the next, that is sign conventions. This is very important area while dealing with the numerical part. Okay, basically the thing is like this. All the measurements that you are going to take in case of this spherical mirrors, that's always going to be from the pole only. That is what the very first point is. All the distances are measured from the pole of the mirror. That is the very first point. All the distance you must make it. That means basically you can take pole as the origin. Alright, now all measurements in the same direction of the incident ray. I repeat, all measurements in the same direction of incident ray from the pole need to be taken as positive, and all measurements in the opposite direction of the incident ray from the pole has to be taken as negative. Okay, now all measurements in the upward direction with respect to the principal axis has to be positive, and all measurements from the principal axis in the downward direction has to be negative. That's all. Okay, moving to the next, that is image formation by spherical mirrors. I repeat, image formation by spherical mirrors. First of all, the image is at infinity. I repeat, image is at infinity. Now object is at infinity. Object is at infinity. So the image will be formed at the focus. Alright. Now what about the nature of the image? It's going to be real, it's going to be inverted and very small. Image will be formed at focus, real and inverted. Alright. Next, the object is kept behind C. That means from infinity the object moved in the forward direction and it's somewhat close to C, and close to C means behind C only. Okay, now you can see the image from F, that means from focus, it moves in the backward direction. So object move in the forward direction, image is move in the backward direction. Again, image is real, inverted and diminished. There it was very small, now here it is diminished. That means the size of the image got increased. Next, this time the object is at C. Now image is also at C. See, object is moving in the forward direction, image is moving in the backward direction, and the size of the image is also increasing. Initially, once the image was formed at focus, it was very small, isn't it? So now this time the size of the image is exactly same as that of size of object. Alright, On top of that, this time again it's real, inverted, and the size is same. Okay, so from F, as it moves in the backward direction, size is also what? Increasing. And second thing is that once object is moving in the forward direction, image is moving in the backward direction. Now in the next, definitely I am going to take the object in the forward direction. That means this time is going to be between C and F, as shown again in the figure. This time it's between C and F. So the image is moving again in the backward direction. That means this time the image is again formed behind C. Again this is going to be real, inverted, and once the object was at C, image was of same size. Now definitely the image will be having, it will be having a bigger size compared to that of the object. That means here again the image is real, inverted, and enlarged, and it is formed behind C only. Alright, next at F. So this time the object is at F. So definitely the image will be formed at infinity. Image will be formed at infinity. So here image is real, inverted, and this time it's going to be very large, and that will be at infinity. Alright, and the next one is this time the object is going to be between F and P. Okay, fine. Here it is between F and P. So once it is between F and P, what happens is here it's going to be virtual. That means the image will be formed behind the mirror. It's going to be virtual, erect, and large in size. Okay, it's erect till this case, till the object was between P and F. The situation was what? The situation was the object was real, it was inverted. Okay, this time the object is virtual and erect. And comparing the size, this time it is an enlarged image. Okay, and next one is the image formation by a convex mirror. Once we are having convex mirror, so all the cases that we discussed in the previous slides was for concave mirror only. This time it is convex mirror. So once I am having a convex mirror, then the image formed by convex mirror, this time it's virtual, erect, and very small in size. Okay, and it's formed at what? F, because the object is at what? Infinity. Object is at infinity, and the image is formed at what? F only. And if I am having a case like this, that means here the object is not at infinity, it's kept at a particular distance from the pole. Okay, then here again image is virtual, erect, and diminished between P and F. That is very, very important. The image is formed between P and F only. Okay, size is diminished, image is erect and virtual. Okay, so that was all about the image formation due to spherical mirrors. We discussed both the case of concave mirror as well as convex mirror, and I believe you are comfortable with that. Now moving to the next, that is refraction of light. So you all know that once light travels from one medium to another one, because of the change in speed of light, the path of the light will be changed, and that phenomenon is known as what? Basically refraction. Okay, so once the light travel from denser to rarer medium, I repeat, once light travel from denser to rarer medium, what happens? It basically bend away from the normal, and once it travel from rarer to denser medium, it bend towards the normal. So in short, how we can understand is, see here this is incident ray, and here this is rarer, and here this is denser. So instead of light going like this, it will bend towards the normal. Okay, and if it is from denser to a rarer medium, if I treat this as a normal, instead of light traveling in this direction, okay, it will bend away from the normal. So I basically treat it like this. For denser medium, moving towards denser medium, bend towards the normal, and moving towards rarer medium, it move away from the normal, provided I treat this as the normal. Okay, this is how in basic level we can understand the thing, or not understand the thing. Basic level you can keep it in your brain just like a tip. Alright, next is law of refraction. Law of refraction, this is also known as Snell's law. So what basically it tells about is, if this is the surface that separates the 2 medium, and if this is the normal, then and if this is the incident ray and here this is the refracted one, this angle is known as what? Angle of incidence, and here this is angle of refraction. Let this be refractive index of medium number 1 and this be refractive index of medium number 2. Refractive index means nothing, the speed of light in this particular medium. Okay, we will be taking the ratio as C divided by V1. Like that means if V1 is the speed of light in this particular medium, okay, now C divided by V1, that's going to be what? Mu1. Alright, now C divided by V2, that's going to be what? Mu2, refractive index. Okay, this is how we calculate the refractive index of the two mediums. Now, how we connect the relation between I and R? That is all about Snell's law. So, the relation is sin I upon sin R, sin I upon sin R, that is equal to mu2 by mu1, sin A upon sin R, that is equal to mu2 by mu1, that is equal to V1 by V2, and that is equal to lambda 1 by lambda 2, provided lambda 1 as well as lambda 2 is the wavelength of the light. Now, we are discussing about the ray optics, but if it is given in terms of wavelength lambda 1 as well as lambda 2, in that case also this equation is valid. Alright, so that is law of refraction, statement number 2, that is Snell's law. Alright, and the very first statement that says incident ray, refracted ray and the normal lies in a common plane. Alright, moving to the next, that is about the refractive index. We already discussed this topic. I just want to discuss about refractive index of water because this might be helpful in many numerical part. Refractive index of water is 1.33 and refractive index of glass is 1.5, and I told you what is refractive index of a medium. Okay, what it is basically speed of light upon speed of the light in air upon speed of light in the given medium. Okay, that is what refractive index basically stands for. Moving to the next, that is relative refractive index. Relative refractive index means nothing. I am having medium number 1 and medium number 2. Light is traveling from 1 to 2. Light is traveling from 1 to 2. Now here, refractive index of second medium with respect to the first. I repeat, refractive index of second medium with respect to the first. That is basically V1 by V2. That is relative refractive index. Alright, moving to the next, that is actual depth and apparent depth. In this case, this is an area of great numerical importance. How to understand this one is, let us have a case like this. Okay, so here light is traveling from medium 1 to 2. So here this is mu1 and let this be mu2. Alright, and here this is rarer medium and here this is denser medium. You all know that treating this as the normal, once it travels from here, it will move away from the normal, and an object kept over here seems to be raised to O dash for an observer looking from this particular point, isn't it? So here if I take AO is the actual depth and AO dash, that is the apparent depth. I repeat, AO is the actual depth and AO dash is the apparent depth. Now how to take the relation between these two is actual depth upon apparent depth. I repeat, actual depth upon apparent depth, that is equal to refractive index of the denser medium upon refractive index of the rarer medium. This is the case where the observer is at the rarer medium, and if the case is something like this, okay, that means this time the observer is somewhere here. So you all know that once the light travels from rarer to denser medium, it bends towards the normal. Okay, so it's supposed to be like this. So if the light is coming from a point like O, for an observer over here, it seems to be coming from O dash. isn't it? So if I take this point as A, now AO is the actual height and AO dash, that is the apparent height. Here apparent height is larger and actual height is lesser. So actual height upon apparent height. I repeat, actual height upon apparent height. Okay, see, it's very simple. Actual height is greater, apparent height is lesser. So actual height upon apparent height, that is refractive index of rarer medium upon refractive index of the lesser medium, because apparent height is greater, isn't it? Apparent height is greater, so that's why it's coming as mu rarer upon mu denser. So basically you just need to understand which is greater and which is lesser. Based upon that you can easily get into that equation. All right, next is critical angle. So once the light travel from a denser medium to a rarer medium at a particular angle of incidence, the reflected ray will move parallel to the surface of separation. Okay, that means here small letter r is equal to what? 90 degree. That particular angle of incidence is known as what? Critical angle. Okay, so if this is taken as critical angle, that means C. So from the relation sin I upon sin R, that is equal to mu 2 by mu 1. Taking this as mu 2 and taking this as mu 1, I can say sin I, this is going to be what? Sin of C, and here this is going to be 1, sin I is 1. That is equal to what? Mu 2 by mu 1. In this way you can get the critical angle for any particular medium. And here critical angle for few materials like diamond, it is 24 degree, and for glass it is 42 degree, and for water it is 48 degree. All right, next is total internal reflection. Once the light travel from denser to rarer medium, and let this be the critical angle C. And if I am having an incident ray whose angle of incidence is greater than critical angle, what happens? The light will be sent back to the denser medium. Okay, that phenomenon is known as what? Total internal reflection. So the condition for total internal reflection over here is condition number 1. Condition number 1, angle of incidence need to be greater than critical angle. Point number 1. Point number 2, the light must be traveling from denser medium to a rarer medium. These are the two mandatory conditions for total internal reflection to take place. Okay, moving to the next, that is refraction at spherical surface. So as we discussed about in the same way as we discussed in the case of spherical mirrors, we were having concave spherical mirror as well as convex spherical mirrors. In the same manner, here we will be having convex refracting surface as well as concave refracting surface. Whether it is convex or whether it is concave, this particular formula is valid in both. That means let this be a convex refracting surface and let this be a concave refracting surface. Okay, I hope you are getting me right. So light is traveling from mu 1, medium number 1 of refractive index mu 1 and medium 2 of refractive index mu 2. Here again it is traveling from medium 1 whose refractive index is mu 1 and towards medium 2 whose refractive index is mu 2. So here you can see again this is basically a part of hollow sphere, sorry, solid sphere, and here again it's a part of solid sphere. So here I am having radius of curvature. This particular surface bear a value of radius of curvature, and here also this bears a value of radius of curvature. So I repeat, light is traveling from 1 to 2. I repeat, light is traveling from 1 to 2. Mu 1 is refractive index of medium number 1 and mu 2 is refractive index of medium number 2. Same here as well, and R is the radius of curvature. So if these are the terms, Then the relation between mu1, mu2, v and u, where v is the image distance, u is the object distance and r is radius of curvature. The relation is mu2 divided by v minus mu1 by u, that is equal to mu2 minus mu1 upon r. I repeat, this is applicable both in the case of concave refracting surface as well as convex refracting surface. Mu2 by v minus mu1 by u equal to mu2 minus mu1 upon r. Alright, u is the distance of the object, v is the distance of the image from the optical center. Here this is optical center and here this is optical center. Okay, I am marking it as O over here. And from the medium at which the object was kept, the refractive index of that is mu1, and the medium at the image is formed, the refractive index of that is mu2. So it is as simple as that. Moving to the next, that is Lensmaker's formula. Alright, so the Lensmaker's formula gives the relationship between f, r1, r2, mu1 and mu2. So let's try to understand what this basically stands for. Here let this be medium number 1 and the refractive index of that is mu1. Here this is mu2 and here again this is mu1. The radius of curvature of the first surface is r1 and radius of curvature for the second surface is r2. Alright, then once I am having a light coming from infinity, okay, after refraction that will be converging onto a particular point on the principal axis. So the distance from the optical center towards that point be f, a focal length. So then 1 by f that is equal to mu2 divided by mu1 minus of 1 into 1 divided by r1 minus of 1 by r2. This is a very helpful formula. Okay, this can be applied in any cases, like for example plano concave, plano convex, all type of lenses you can apply this particular formula. So here this is the standard equation and that's what we call it as what? Lensmaker's formula. Next is thin lens formula. Okay, thin lens formula says 1 by f that's equal to 1 by v minus of 1 by u. Thin lens formula. Next is power of lens. Power of lens is basically P is equal to 1 by f, and what about the unit? The unit is diopter represented by capital D. Next is image formation by convex lens. Alright, so here as what we discussed in the same way we discussed in the case of that spherical reflecting surface, here for lens we are discussing. First of all, see, as I told you, first we are going to discuss about the image formation of convex lens. This time the object is at infinity. Object is at infinity and where the image is formed, it's at f. Okay, that means at the principal focus, that is f2, alright, and the image is real, inverted and extremely diminished. It's real, okay, inverted and extremely diminished. And if from infinity, if it is moving in the forward direction, the image will move in the backward direction. Okay, so here between f2 and 2f, okay, between f2 and 2f, the position of the image, alright, and here image formed is what? Real and inverted. So here the object is coming in the forward direction, okay, image is moving in the backward direction. So here it is coming in the forward direction, here it will move in the backward direction. That's what you can see. From f2 it shifted towards what? A position between f2 and 2f2. Okay, now in the next, here this time it is at 2f1. Okay, fine. So where the image is formed at 2f2. Okay, and this time see again the image is real, inverted, and regarding the size, it is as of same size as of the object. So here, just try to understand the thing. Once it was at focus, the image was extremely diminished. Object coming in the forward direction, image is moving in the backward direction, and size is increasing. You can connect the case with the image formation case of what? Concave mirror, isn't it? Yes. Now, this time the object is between 2f1 and f1. 2f1 and f1. So definitely what will happen? Object is moving in the forward direction, image should move in the backward direction, isn't it? So here, this time the position of the image, it is behind 2f2. It is behind 2f2, real, inverted, and this time definitely magnified. Once it was 2f1, the image was formed at 2f2, okay, and the size was same. Now object got moved towards 2f1, between 2f1 as well as f1. So the image moves in the backward direction. This time size got increased. And next is at f1. Okay, last time it was between 2f1 and f1, and here it is at f1, isn't it? So here this is f1, not f2. All right. So the image will be formed at definitely infinity, real, inverted, and highly magnified. It is going to be, and at last it's between the optical center and f1. This time the object is between optical center and f1. So here the image form this time is not real, but it is virtual. You can see the image is erect and magnified. Okay, so the image formed is erect, all right, erect, virtual, and highly magnified. Okay, next is for a concave lens. That means image formation due to a concave lens. Once the object is at f, once the object is kept at f, okay, I think I said the object is kept at f, sorry, the object is kept at infinity. Object is kept at infinity. Where the image will be formed? Definitely it will be formed at the focus, because it's going to diverge like this, and it seems to be coming from this particular point. Okay, so the once object is at focus, the image formed is virtual, erect, and point sized. Okay, and if it is between say optical center and f2, all right, that means anywhere except on the principal axis. Other than this, it's between, it's going to be virtual, and it's going to be, the image is going to be between where? See, here the object was, okay, and the image is going to be between optical center as well as f2. All right, so it's moving in the forward direction. And next is combination of lens. So here you are having two cases for the case of what? Concave lens. One is the object is at infinity, and second one is between any point, like in front of any point, at any point in front of the optical center. Next is combination of lens. If I am having two lenses of focal length f1 and f2, okay, if I am having two lenses of focal length f1 and f2, then the effective focal length is supposed to be 1 upon f equal to 1 upon f1 plus 1 upon f2, provided they are kept very close to each other. Okay, so since the relation of focal length was 1 by f equal to 1 by f1 plus 1 by f2, we already discussed the relation between focal length as well as the power. So effective power P is going to be what? P1 plus P2. Now, if these lenses are kept at a distance of separation of say small letter d, lens L1, lens L2, focal length f1, focal length f2. If this is the case, then 1 by f is going to be 1 by f1 plus 1 by f2 minus of d into f1, f2. All right, if d is the distance of separation. So since this is the relation for focal length, power can be connected as what? P equal to P1 plus P2 minus of d into P1, P2, where P1 as well as P2 are the power of lens 1 as well as lens 2 respectively. Okay. Moving to the next, that is linear magnification of a lens. Linear magnification of mirror we discussed as what? M equal to minus of V by U. Here this time it is plus V by U. There's only difference. Now axial magnification. Alright, axial magnification, here this time it's going to be dV by du, dV by du, that is V by U the all square. As what we discussed in the earlier case, just a difference in the, just because of that mirror formula as well as lens formula there is a difference. So just because of that, while replacing V as well as U, the same difference you can have here as well. So in terms of U, if I want to write this, there it is going to be F upon F plus U, or it can be written as F minus of U divided by F the whole square. Okay, and we are discussing about the case of what? Axial magnification. The case of axial magnification it was. Alright, moving to the next, that is cutting a lens. We have got two provision. Either you can cut the lens like this, otherwise you can cut the lens like this. Okay, case 1 as well as case 2. Both the cases are mentioned here. So if the lens is cut like this, the first half that will be having focal length as 2f, second one also will be having it as 2f. Alright. Now, if it is cut like this, then the upper half that will be having a focal length as f only, and the lower one is also going to have a focal length as f. Isn't it? Now this case, it's nothing, that lens that we cut into two half, f as well as f. Now it is kept like this. That means the first lens is kept in this manner and the second one is kept in this manner again. So the effective focal length is going to be what? F. And here, this earlier it was like this, now we are just flipping that one, again it's going to be F. Now this was the first part and here there was the second part and we are combining it like this. So the effective is going to be F by 2. And if I combine it like this, the effective focal length is going to be infinity. Okay, so that was about the cutting of lens. Next is prism. Okay, so here it's a triangular prism. So you can see this is the incident ray. Here take place the first refraction and here second refraction. So here this is known as the emerging ray. Here this is the emerging ray and here this is the incident ray. So the angle between these two, this is known as angle of deviation, and that is a matter of great importance. So how we connect the angle of deviation as well as refractive index of the prism? The first relation is mu is equal to sine of a plus dou upon 2 upon sine of a by 2. I repeat, sine of a plus dou by 2 upon sine of a by 2, where dou is the angle of minimum deviation. Angle of minimum deviation means, actually what happens is, if I keep on increasing the angle of incidence, the angle of deviation decreases and it reaches to a minimum value. So that is angle of minimum deviation. Alright, so that is the first relation. And if we are having a small angle prism, and okay, I forgot to tell about this capital A. Capital A is the angle of the prism. That means here this is refracting surface number 1 and here this is refracting surface number 2. The angle between these two is taken as capital A. So capital A stands for angle of the prism. And if we are having a small angled prism, then in that case the angle of deviation, dou suffix m, that can be written as what? Mu minus of 1 into capital A. Alright, so two relation. First one is mu is equal to sine of a plus dou by 2 upon sine of a by 2. That was relation number 1. And for a small angle prism, dou is equal to mu minus 1 into capital A. Again, capital A is angle of prism only. Alright. Moving to the next, that is simple microscope. So in this case of optical instruments, we are having simple microscope, then compound microscope as well as telescope. Alright. So in all these three cases, we are basically discussing about the magnification. Alright. Or magnifying power. So if we are having a simple microscope, okay, then case number 1, if the final image is formed at least distance of distinct vision. I repeat, final image is formed at least distance of distinct vision, then magnifying power m, that is equal to 1 plus d upon f. I repeat, 1 plus d upon f. And if the image is formed at infinity, there the image was formed at least distance of distinct vision, and here the image is formed at infinity, then it is d upon f only. This one won't be there. Basically it is m equal to d upon f. Alright. Now moving to compound microscope, again if the final image is formed at least a distance of distinct vision, here this time it is v suffix o upon u suffix o, where v suffix o is the image distance with respect to the objective lens, and u suffix o is object distance with respect to the objective lens, into 1 plus d upon fe. Here it was d upon f, here it is d upon fe. Okay, and if the image is formed at infinity, again like one was missing here, here also that one portion, that means this part will be removed, and here it is going to be m is equal to vo upon u into d upon fe. Alright. Now in case of astronomical telescope, if the image is formed at least distance of distinct vision, here it was vo upon u, here this is fo upon fe, fo upon fe into 1 plus d upon fe. And if the image is at infinity, alright, this entire part will be missing, it's going to be fo upon fe. Alright. And next is reflecting telescope. So in this particular thing, so here in case of astronomical telescope, we are having one objective and eyepiece like this. Okay, basically you must understand the structure, and here we are this is the ray coming, and here we are having a concave mirror. Okay, and from that concave mirror it's striking onto a plane surface, and here we are having a convex lens which is acting as basically an eyepiece. So in that case, the magnifying power m is equal to fo upon fe, fo upon fe. Alright, so that was of reflecting telescope. Okay, so in case of optical instruments, we have got three. First one is simple microscope, next one is compound microscope, and third one is telescope. And in case of telescope, we have got two categories. First one is astronomical telescope, and next one is reflecting type telescope. In case of reflecting type telescope, we calculated the magnifying power as fo upon fe. And here in case of astronomical telescope, we are having two case. Image is formed at least distance of distinct vision, there we got it as fo upon fe into 1 plus d upon fe. And once the image is formed at infinity, we got it as fo upon fe. Alright. Now we need to move to the next, that is wave optics, chapter 2 of this module. So here first of all we need to tell about the Huygens principle. So Huygens principle says that every point on the primary wavefront act as a source of what? Another wave, which is known as secondary wave, and this secondary wave keep on growing like this, travel in all possible directions, and once we form another, once we give another envelope, this acts as a secondary wavefront, and every point on this secondary wavefront again act as a source of another wave, and it will keep growing like this, and this will be the next secondary wavefront. Alright, so basically all this point tells this thing. Okay, that is Huygens principle. And while telling about the wavefront, depending upon the source, depending upon the source, we can have three categories. First one is spherical wavefront for point source, cylindrical wavefront for linear source, and plane wavefront, source kept at infinity. Okay. Now, next is superposition of wave. That means if I have a point P here, okay, wave number 1 is reaching here and wave number 2 simultaneously reach here. So here this is wave number 1 and here this is wave number 2. If wave number 1 was individually passing through point P, it should have created a disturbance of Y1. And if wave number 2 was individually passing through point number P, it should have created a displacement of Y2. Now once both the waves are simultaneously passing through point P, the resultant displacement created Y, that need to be equals to what? Y1 plus Y2. Okay, then once two such waves are reaching there, okay, the particle at that particular point, okay, or the energy variation at that particular point can be considered same as that of a simple harmonic motion, which will be having an amplitude as capital A. Okay, and that resultant amplitude A, that's going to be root of A1 square plus A2 square plus 2 times A1 A2 cos of phi. Alright, where A1 as well as A2, I told you we were having two different waves, Y1 as well as two different waves was there, wave number 1 as well as wave number 2. Wave number 1 is having an amplitude of A1 and wave number 2 is having an amplitude of A2. Okay, in that case, the resultant amplitude, okay, the resultant amplitude is going to be A equal to A1 square plus A2 square plus 2A1 A2 cos phi. And what about the intensity? Intensity is going to be I, okay, that's equal to what? I1 plus I2 plus 2 times root of I1 I2 cos of phi. And you might be wondering, what is phi? Basically, phi is the phase difference between wave number 1 as well as wave number 2. Okay, so these are very important relations. And now, if these two waves reach simultaneously onto a particular point, okay, the effective displacement, okay, the effective displacement, whether it is got increased or whether it is got decreased, based on that, we can consider this particular combination or the superposition principle as constructive as well as destructive interference. So basically, interference is the superimposing of one wave over the another one, that is known as interference. All right, now if the resultant amplitude is being increased, the disturbance altogether, the disturbance got increased, then it is known as constructive interference. And altogether, if the disturbance is decreasing, then that is known as what? Destructive interference. So if you want the disturbance to be increased, definitely this term need to be positive, and if it is decreasing, that means this term need to be negative. So for constructive interference, cos phi need to be positive, and for destructive interference, cos phi need to be negative. That is also a very helpful information. All right, next is Young's double slit experiment. So basically, this particular thing, what all we studied over here, that means two waves simultaneously reaching onto point P, and point P is getting a different type of disturbance individually due to wave number 1 as well as wave number 2, and altogether it is having a different mode of vibration, and that vibration is also going to be a simple harmonic motion, isn't it? So all these things are taking us to the next concept, that is Young's double slit experiment. So you know that in this particular arrangement, we are having two slits, S1 as well as S2. All right, so the waves are coming and reaching onto point P. All right, so depending upon the path of the wave that is traveling from S1 to P and S2 to P, there will be a path difference created. All right, and the distance from the central maxima towards this, if I mark a small letter y, and distance between the slit and the screen is marked as capital D and the distance between these two sources is marked as small letter d, then I can have a relation as path difference delta P. Here it is, delta P is equal to y small letter d upon capital D. Alright, and if here the intensity is increasing, that means if it is constructive interference, that means for the maxima, constructive interference means the intensity is decreased and destructive interference means the intensity is decreasing. And if it is a completely bright fringe, that means that is the best version of what? Constructive interference. And if it is a completely dark, that means it is the best version of destructive interference. So for the best version of constructive interference, we need to have cos phi as +1. And for the best version of destructive interference, we must have cos phi as -1. Alright, so what I said, cos phi equal to 1, that means bright fringe, and cos phi equal to -1, it is dark fringe. S1 and as well as S2, they are identical source. That means here A1 is equal to A2 equal to what? We can take it as A, or you can say I1 equal to I2, you can take it as I0, because sources are identical. Alright, then in that case, you all know that for cos phi need to be 1. For cos phi need to be 1, we must have the value of phi as what? Either it could be 0 or it could be 2 pi, 4 pi, etc. And for cos phi, that need to be -1. We must have the value of phi as pi, okay, 3 pi, 5 pi, etc. Alright, now for a phase difference of 2 pi, the path difference is what? Lambda. For a phase difference of 2 pi, path difference is lambda. Then for a phase difference phi, the path difference is going to be delta P, that's equal to what? Phi times lambda upon 2 pi. Okay, and if the path difference, I told you, if the path difference is lambda, okay, if the path difference is lambda, in this case just try to understand the situation over here. If it is pi, 3 pi and 4 pi, I am telling about the phase difference. Okay, pi, 3 pi and 5 pi, it's going to be destructive. And if it is 0, 2 pi and 4 pi, it is going to be what? It's going to be constructive interference. I mean the bright fringe over here. Now just try to understand the situation. If I have got phi, okay, as 0, if I got it as 0, then path difference is also going to be 0. That means if the path difference is 0, it's going to be bright. And next, go for the another one. Let me take phi as, see, the first case was what? 0. Now let me take it as what? 2 pi. So once it is 2 pi, it's going to be what? Lambda. Because phi is 2 pi and 2 pi will cancel. Path difference is going to be lambda. If I go for the next, that is 4 pi, that means it's going to be 2 times lambda. So basically, if delta P is equal to 0, lambda, 2 lambda, 3 lambda, etc., it's going to be a bright fringe. And if delta P is equal to 0, okay, then lambda by 2, 3 lambda by 2, 5 lambda by 2, etc. It's going to be what? Not 0. Lambda by 2, 3 lambda by 2, 5 lambda by 2, it's going to be what? A dark fringe. Because just have a look. Here, if I have got delta P is equal to, instead of phi, what I am going to have? I am going to have it as pi this time. Pi, okay, pi lambda upon 2 times pi. So pi and pi will cancel each other. So lambda by 2. So for path difference, delta P is equal to lambda by 2, 3 lambda by 2, 5 lambda by 2 extra, it's going to be dark fringe. That is how I am having that relation over here. The position of bright fringe, y suffix bright, that is n lambda capital D by small letter d, and for y suffix dark, that means position of dark fringe, it is 2n minus 1 into lambda capital D divided by 2 times small letter d. Basically this is the same. It's the same. So next is fringe width. The distance of separation between two successive bright fringe or two successive dark fringe is known as what? The fringe width, the relation for that one is beta is equal to lambda capital D divided by small letter d. And what about the angular width? That means angular width, see, if this is a bright fringe, here this is the linear width and here this is the angular width, theta. So theta is basically lambda by small letter d or beta divided by capital D, that's all. Arc by radius, that is the concept that we are using in this case. So next is intensity of the fringes. That means in Young's double slit experiment, I told you we are going to have bright fringe, dark fringe, bright fringe, dark fringe, like that. Okay, so there, how to calculate the intensity? So for the bright fringe, that is the portion where we are having the maximum intensity. So that is going to be I max, that equal to 4 times I naught, where I naught is the intensity of the wave coming from any one of the slit S1 or S2, and I minimum definitely dark fringe, that is going to be 0. And if you have got any point P, okay, where you know what is the phase difference between the wave coming from S1 as well as S2, in that case the resultant intensity I, that is going to be 4 times I naught, where I naught is the intensity of the wave coming from S1 or S2. So there it is going to be 4 times I naught into cos square phi by 2, where again I am repeating, phi is the phase difference between waves coming from S1 as well as S2. Moving to the next, that is, what if we insert a slab of thickness T onto, or insert a slab of thickness T in front of the wave coming from S1 as well as S2. Okay, I am inserting a slab like this. Here this is of thickness T and refractive index mu. If I am inserting it in the upward direction, so here what happens, you know, earlier if this was the position of fringe, say F1, it will shift in the upward direction through a value of delta y. And if it's inserted in the downward, like for the wave coming from S2, it will shift in the downward direction, and if we put for the slit in front of the slit in the upward position, it will shift towards in the upward direction. Okay, so that shift delta y, this is going to be, I told you, T is the thickness, mu is the refractive index. Then in that case, delta y is going to be capital D divided by small letter d. Again, capital D is this distance and small letter d was the distance of separation between these two slits. Okay, so delta y is equal to capital D upon small letter d into mu minus of 1 times small letter t. This is the relation, that means the shift in the fringe. Okay, in terms of beta and lambda, where in terms of fringe width beta and wavelength lambda, if you want to explain, capital D is going to be replaced by beta and smaller d is going to be replaced by lambda. That is the only relation. Alright, moving to the next, that is diffraction. Diffraction, we have got two type of diffraction. First one is Fresnel and second one is Fraunhofer. The differences are, for Fresnel's diffraction, the source is at infinite, and Fraunhofer, the source is at finite distance. Second, for Fresnel's, we does not need any optical instruments. Okay, and for Fraunhofer, we need optical instruments. Alright, and for the fringes, in case of Fresnel's, the fringes are of not sharp as well as well defined, but in case of Fraunhofer, the fringes are sharp as well as well defined. And for the further studies, we are going to consider Fraunhofer's diffraction. So in case of Fraunhofer diffraction, just wanted to give a rough idea with the figure as well. So let this be a wave coming from the upper edge, and then let this be a wave coming from the lower edge, and here this is getting interfering at point P, and you all know that this is the path difference, where this is the distance and this angle is theta. So this is the width of the slit, small letter d, and here capital D is the distance towards the screen. All right. Now the path difference. The path difference delta P, that's going to be d times sine theta, which is approximately equal to d theta, that is equal to n times lambda for secondary minimum. All right. And the same thing, delta P, that is equal to d times sine theta, that is equal to approximately d times theta, that is equal to 2n plus 1 by 2 times lambda for secondary maximum. Secondary maxima. See, here this was for secondary minima, and here this is for secondary maxima. And regarding the fringe width, so how to calculate the angular width now? You can connect these two relation, and in case of maxima you can connect these two, and in case of minima you can connect these two. And regarding the angular spread of central maxima and the secondary maxima, the thing is secondary maxima is having half the angular spread of central maxima. That is also a very important relation that you must understood. Next is polarization. So let me consider an unpolarized light coming like this. It is having an intensity of say I0. Once it is passed through a polarizer like this, all right, once it is passed through a polarizer like this, then what you are going to have over here is plain polarized light. So here the intensity was I0. So here the intensity will be reduced to half of that, that is I0 by 2. And if I place an analyzer here like this, okay, now if they are, that means if these two axes are kept parallel, then the light coming out here is again going to have an intensity of I0 by 2 only. I0 by 2 only. And if it is turned through an angle theta like this, if it is turned through an angle theta like this, then the intensity is going to be I dash, that is equal to I0 by 2. That means whatever the intensity it was there, I0 by 2 into cos square theta. And this is what we call it as what? Malus law. All right. Next is Brester's law. Brester's law says if this is a refracting surface, if this is a refracting surface, and here this is an unpolarized light coming, okay, and at a particular angle of incidence, light got refracted like this and reflected, partially transmitted, partially refracted and partially reflected. If the angle between this is 90 degree, if the angle between this one is 90 degree, then what I am going to have here is a plain polarized light, and definitely the transmitted light is unpolarized. So here this is a plain polarized light. So here the angle need to be what? 90 degree. So this particular angle of incidence at which it was happening, so okay, if I mark it as I suffix p, then I suffix p plus r, where r is the angle of refraction, that need to be what? 90 degree. Okay, and the angle at which such a plain polarized light is going to be retrieved from that reflected one, then what has to be that angle of incidence? Okay, then for that we have got a relation between I and the refractive index of the material, I mean this that medium, through which that refracting was happening, and that relation is mu is equal to tan of I suffix p. Mu is equal to tan of I suffix p, and that is what we call it as what? Brister's law. So once again I repeat, here this is the incident light, okay, that was unpolarized, and at a particular angle of incidence, okay, it was observed that the refracted light, that is unpolarized, but the reflected ray seems to be plane polarized, okay. In that condition, I suffix p plus r need to be equal to 90 degree, and for which angle of incidence the reflected ray is going to be plane polarized. How we can find out that relation? That completely depends upon the refractive index of the material, and how it depends, mu is equal to tan of I suffix p. All right, moving to the next, that is dual nature of radiation and matter. It's a very small chapter. First of all, we need to discuss about the relation between work function, threshold frequency as well as threshold wavelength in case of photoelectric effect. The relation is phi, that is work function, that is equal to h into nu, where nu is the threshold frequency, that is equal to hc divided by lambda max, where lambda max is the threshold wavelength. Next is Einstein's photoelectric equation. Basically that is law of conservation of energy only. Now here the thing is, the kinetic energy of the photoelectrons coming out, that is k max, that will be equal to h into nu, that is the energy of the incident radiation minus work function. I repeat, the kinetic energy of the electron coming out, I take it as k max. So the energy being possessed by that electron is going to be energy of the incident radiation h into nu minus of what? Minus of work function. Alright, in terms of threshold frequency, if I want to say, that's going to be h into nu minus of h into nu naught, where nu naught is the threshold frequency. Next is stopping potential. Stopping potential is the potential that we need to apply to completely stop this photoelectrons. So, okay, so that means the energy that we are spending, that must be equivalent to the maximum kinetic energy. So that is why kinetic energy, maximum kinetic energy of photoelectron, if I take it as half of mv square, that is equal to E into V naught, where V naught is the stopping potential. Alright, next comes the graph, that is very important. Photoelectric current versus intensity. More the intensity, more number of photons striking, more number of photons striking, more number of electrons will be coming out. That means they are directly proportional. Photoelectric current as well as intensity, they are directly proportional. Next is variation of photoelectric current I versus potential difference but constant frequency. That means frequency is kept as the same and intensity is increasing. So if the intensities keep on increasing, then what will happen? The Imax value will keep on increasing, isn't it? Now frequency remains the same. So once frequency remains the same, what happens? Stopping potential be the same, because frequency has got direct relation with the energy. So energy remains the same, intensity is increasing. So intensity is increasing, stopping potential is going to be the same because frequency is not changing, and since intensity was increasing, Imax will be keep on increasing. All right, now in this case intensity kept constant and frequency is increasing. Once frequency is increasing, what will happen? Stopping potential will keep on increasing. So stopping potential, you can see it's moving in the backward direction. Since intensity remains the same, the maximum value of current is not at all changing. That is common for all the three radiation in this case. Next is stopping potential versus threshold frequency. Basically it's going to be a straight line where we are having stopping potential on y-axis and frequency on the x-axis, and here you are having a y-intercept, that is minus of phi naught upon E, where phi naught is what? The work function, and here you can have the threshold frequency. And the slope of this particular stopping potential versus frequency graph, the slope is tan theta equals tan of theta equals h by E. You know that this is a constant. This is a constant. All right. Next is the frequency versus photoelectric current. It has got no relation. That's why it's a straight line. Next is intensity versus stopping potential. Again, not at all connected. You can see it's not depending at all. Next is photoelectric current versus time lag. So it's initially it is increasing, and after that This is not at all affecting. All right. And the last one is matter wave or de Broglie wave. Basically, it says for any particle having a linear momentum p, then definitely there will be a wave associated with that particular particle, and lambda that is equal to h upon p. This is the standard relation. This is a standard relation where p is the linear momentum, and we know that p is equal to m into v. So there we have got another form of this, that is h upon m into v. All right. Then we know that kinetic energy is equal to half of m into v square. If I multiply with m as well as divide by m, so here 2 times m into kinetic energy, 2 times m into kinetic energy, that is basically p square. So p is equal to what? Under root of 2 times m into k. All right. So you have got another version. All right. That means wavelength lambda is equal to h upon, instead of p, I can have what? Under root of 2 times m into k. And kinetic energy k, that is equal to what? Stopping potential into E. So once I replace k, then I am going to get it as what? See, E into V. All right. And if I want to represent it for thermal neutron, it's having energy of 3 by 2 kBt. So once I replace kinetic energy by 3 by 2 kBt, there I am going to have the expression as h upon under root of 2 times m into k suffix, 3 times m into k suffix b times t. All right. So that was all from the recap video of physics for this module. I wish you are going to perform extremely good in this particular upcoming test. We will be coming with a detailed solution of your test after the examination. Till then, take care. Bye bye.